Okay. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another session, and today we are talking about booklet 19, which is about conservation of momentum and collisions. So let's get on with it. Bismillah. Here I'm just going to write what I usually write, which is answers and notes. Okay, fantastic. And let's change this color to something a bit more friendly, perhaps light blue. Okay, Bismillah ar-Rahman ar-Rahim. So what's this about? We're talking about conservation of momentum, and what that means is basically saving momentum. What do we mean by that? What does that actually mean? Well, what it means is that it stays the same. Okay, so momentum stays the same within a system. And that will make sense in just a moment. Let me just read through this. So like energy, momentum is conserved. You cannot create momentum. You cannot destroy it. You can only transfer it from one form to another. Okay, so the total momentum in the universe always remains the same. In this lesson, you will learn how you apply conservation of momentum to common everyday situations. Okay, so we'll find out about that in a minute. So just a quick recap. Momentum is obviously equal to momentum we refer to as P. Remember that's from the word pello, which is to strike, or pelleri, which is like a moment of striking. Momentum refers to is equal to the mass times the velocity. Okay, that's momentum. Momentum equals to mass times velocity. Now we also have something called change in momentum, which is impulse. And that equals force times time, or Pf minus Pi, or P final minus P initial, or basically final momentum minus initial momentum. Okay, so that is a quick recap of what we've been doing. Okay, so if the total force is zero, then the initial and the final momentum must be the same. Okay, so here we're talking about something else, and this is a situation that happens when there is no external force acting on something. So I'll just give you a quick example. If an object is not moving, then obviously the total force acting on the object is zero, right? So the net force acting on the object is zero. So this is a situation, for example, if a book is sitting on the table, there is weight force acting down, there is a normal force acting up. They balance each other out. There is no push, there is no pull. The book is not moving, it is static. Therefore, the total momentum acting on the book is zero. Okay, so if there is no external force, then the momentum is equal to zero. And this is what this is saying here. This is what this statement here is saying. If the total force is zero, then the initial and the final momentums must be equal, and therefore there is no impulse, there is no change in momentum. Okay, what about a different situation? What about an object that is moving at constant speed? An object that is moving at constant speed also experiences no external force. How is that? Let's have a look. I'll show you an example. So let's say an object is moving at constant speed, right? So here's a ball, and the ball is moving at constant speed in this direction. And I want to calculate the impulse. Impulse, remember, is equal to final momentum minus the initial momentum. So what's going to be the formula for final momentum? It's going to be mass times Vf, and then initial momentum is going to be mass multiplied by Vi. Well, I think some of you have already figured it out. Both Vf and Vi are the same if it's moving at constant speed. So if the object is moving at constant speed of 2 meters per second, and it has a mass of 1 kilogram, then obviously the final momentum is going to be 2 kilograms dot meters per second, and the initial momentum is going to be also 2, and you can see there is no impulse. It equals 0 because 2 minus 2 is 0. So these are the two situations where there is no impulse. If the object is not moving, which means the speed is 0, and therefore the momentum is 0, and the impulse is 0. Or if the object is moving at constant velocity or at constant speed, then obviously the final speed and the initial speed are 1 because there is no change in speed. And so therefore there is no change in momentum. Momentum in the beginning and the end is going to be the same. And so the final momentum minus the initial momentum will equal 0. So those are the two situations when there is no impulse. If the object is not moving, or if the object is moving at constant speed. And I think some of you might have figured out that is literally the definition of acceleration, right? So if the object is not accelerating, it's either, if it's not experiencing an external force, it means it's not accelerating. There is no change in velocity whatsoever. If it's sitting still, there's no change in velocity, and if it's moving at constant speed or constant velocity, then there is also no change. Okay, let's move on. Internal and external forces can act on a system. Now, what do we mean by a system? So let me tell you something. A system is anything that we want to choose to be a system. So that's the first thing I want you to try and get through your head. If we are talking about a person shooting a ball, the foot and the ball can be a system. So we're talking about a bubble, like we're analyzing a portion, a part, an ensemble, like a just that part. That's what we call a system. So basically anything can be a system that can be part of a bigger system or whatever. So this is what we refer to in physics, at least when we're talking about systems. We're talking about an interaction between two or more objects that we choose, okay? And hopefully that'll make sense as we go on. So let's say, for example, this bicyclist here, or this biker, or this cyclist, that is a system. So we can refer to this as a system. So the cyclist and her bike are one system, right? So there are internal forces acting on the system, and there are external forces acting on the system. And the internal forces acting within a system do not can change the magnitude of the force, can change the magnitude of the acceleration, but overall the momentum is conserved within the system. So what we mean by that is, for example, if you are traveling in a car, right? You're traveling in a car, and suddenly you started, let's say jumping up and down within the car. Or let's make this example slightly more interesting. Let's say you're traveling on a plane and you started running backwards in the plane. Okay, now here's the thing. The momentum of the plane is moving forward, yeah? So the plane is moving forward with all the passengers and all the luggage and everything else. Here's the plane. It's moving forward. The plane has a mass of, let's say, for example, 30 tons. So 30,000 kilograms. And it's moving at a speed of 500 kilometers an hour. Okay, so basically, or let's make it in meters per second. Approximately, I can't do it right now, 500 divided by 3,600, so approximately, what's going on here, 500,000 divided by 3,600, so it's approximately 140 meters per second. So let's say the plane is moving with a speed, so this is the mass of the plane, and the speed of the plane, the velocity is equal to 140 meters per second. So that means the momentum of the plane is going to be mass times velocity is going to be 140 multiplied by 30,000. Okay, so it's about 4.2 times 10 to the power of 6 kilograms per meters per second. Now here is the situation that we're talking about. If somebody is on the plane and they are moving backwards, or they are jumping. Now they have a momentum, obviously. If they are moving backwards on the plane, let's say here's the person and they are moving that way, okay, and they are moving this way. Let's say they're moving this way at 3 meters per second and they have a mass of about 50 kilos. Then obviously they have a momentum of about 150 kilograms per meters per second. Does this affect the momentum of the plane moving forward? No. Whatever's happening inside the plane is part of that system, right? So it's a bit like saying, for example, I'm running. What is my momentum? It's my mass times my velocity. And then somebody might come along and say, well, hang on, your blood is flowing, and it's not flowing in the same direction. And there's also like some gut bacteria, and so is my momentum changing? No, my overall momentum of the system stays the same. Okay, so even though the momentum inside me might be different, even though the momentum inside the plane might be different, overall it is conserved. Overall, it is conserved. So basically, it will remain the same within the system. Okay? So let's have a look at another example here that the book has chosen. Internal and external forces can act on a system. One day, you take a bicycle out for a ride. Let's say that you and the bicycle are a system. So you and the bicycle are a system, right? So, but I want you to notice something here. Let's say. So that means we choose it. We choose what a system is. So it's very important. Let's say that you and the bicycle are a system and that everything else is outside. Okay, so here we are. We have this situation here. So these two are a system, but not everything outside. So many forces act on you and the bicycle, and it's useful to distinguish between those that are internal to the system and those that are external to the system. So anything internal to the system basically refers to anything that is happening between the bicycle and the person and the bicycle. And anything outside of that is external to the system. But let's read through this and see if we can make sense of anything else. So internal forces act between objects within a system. So in this case, we've got the cyclist and the bicycle. If you push forward on the handlebars as you ride, you exert an internal force between you and the bicycle. So over here, for example, this person here, you see her hands, and she is exerting a force on the bicycle, right? But here's the thing, at the end of the day, the bicycle is also going to push back on the hands of the cyclist. So the cyclist is pushing on the bicycle is pushing back on her, and these forces are equal and opposite, as we know from Newton's third law. So that's what it's saying here. The handlebars push back, and they are equal and opposite, and therefore they cancel each other out. These are internal forces because the handlebars are both in the system, and so it doesn't really matter. Okay, it's basically like saying if this person becomes tired, right? If this cyclist becomes tired, what is she going to do? She's going to sit on the seat. So there's a weight force acting down, and there is a normal force acting up from the seat. But it doesn't matter. It doesn't matter if she's sitting down on the seat or if she's applying the force on the pedals. It's part of the system. It doesn't matter. Okay, it's all part of the same system. So whether she's putting the force down on the handlebars and the pedals or she's putting it down on the seat, it is all part of the same system. It doesn't change a thing. Alternatively, we can have external forces, and external forces are slightly different. So external forces, on the other hand, are exerted on the system by something outside the system. And this is important, okay? Now, those can stop something, they can change the direction, they can stop the object, they can speed up the object. So those are the kinds of forces that can change the object's speed or velocity, and or alternatively can stop the object. Okay, so they can either slow it down, speed it up, change the direction, which means changing the acceleration, slow it down, speed up, or change the direction, or they can also cause it to stop completely. So external forces, on the other hand, are exerted on the system by something outside the system. So let's say, for example, somebody throws a ball at the cyclist. That is an external force. The road with friction, that is an external force. Why? Because the road is not part of the system, right? The air, that is an external force. Okay, that is not part of the system. A fly, that is an external force. All of these are examples of external forces. When you pedal the bicycle, the rear tires exert a force against the road, and the road exerts an equal and opposite force against the tire, as indicated in figure 7.8. This is figure 7.8. Okay? Since the road is outside the system, the force exerted on the tire is an external force. Similarly, the force of gravity pulling down on you and the bicycle is an external force. All right, so there is a weight force acting down and there is a normal force acting up. But remember, you and the bicycle together, combined, are being acted upon by external forces, namely gravity. So gravity is pulling you and the bicycle down. That is an external force. That is an external force. Hopefully that'll make sense once we do some questions as well. Why do you always zoom in when I don't want you to zoom in? Here we have an example that we must do, and let's do it. Why not? Two groups of canoes. Here's a group, and here's a group. Two groups of canoes float motionless in the middle of a lake. Okay? After a brief visit, someone in canoe 1 pushes on canoe 2. So here's canoe 1 and here's canoe 2. Someone in canoe 1 pushes on canoe 2 with a force of 46 newtons. Now the force lasts for 1.2 seconds. All right, so this is what we need to do. Force equals 46 newtons and time equals 1.2 seconds. And moves the canoes in opposite directions. What is the momentum of each canoe after you push? Easy. Right, so what is the momentum of each canoe after you push? Well, we know that momentum or change in momentum is equal to P final minus P initial. The final momentum minus the initial momentum. Remember, read the question carefully because the clues are in the question. Two groups of canoes float motionless. So that means they start from rest. They start from rest. So Pi equals, the initial momentum is 0. The initial momentum is 0. Why is that? Because the velocity, remember, what is momentum? Momentum equals mass times velocity, my final velocity, and here it's going to be mass times initial velocity because it's the initial momentum. Since this guy here is equal to 0, then the whole thing over here, Pi equals 0. This equals 0, right? Because it was motionless. So basically, in that case, change in momentum equals only P final. And that's what it's asking for. What is the momentum for each one? So now that we know that, so change in momentum is basically just Pf minus 0. Well, I also know that change in momentum is equal to impulse, remember? This is impulse. Impulse equals change in momentum. And another formula for that is this. Change in momentum equals force times time. Do we have the time? Yes. Do we have the force? Yes. So what do we need? We need to work out the impulse. It's going to be 1.2 times 46.2 times 4 is 8 plus 0.2 times that is equal to, so that'll be about 55. 1.2 times 46 is almost exactly 55. So that is what that is going to be. Change in momentum equals 46 times 1.2, which is force times time, and that is equal to 55. And what is the unit in this case? Well, we can go with that for a change. This is an acceptable unit for impulse. This is also an acceptable unit for impulse. Because remember, impulse is equal to mass times velocity. So it's kilograms dot meters per second. It's also equal to force times time, which is newtons per second. Okay, so that's how we answer that one, and that's the answer to that one. Now, hang on a minute. Someone might be saying, wait a minute. They asked for the momentum of each canoe, not just one. Yeah, so basically over here we'll take 46 multiplied by 1.2 multiplied by 1.2, and over here we'll take negative 46 multiplied by 1.2. Why negative 46? Well, because it's going in opposite directions. And so one of them is going to be negative 55, while the other one's going to be 55. Now at this stage someone's asking me, why did you take this as positive and why did you take this as negative? It's all arbitrary. So over here you can see the x, the x-axis, all right? And over here that's the positive x-axis, and over here that's the negative x-axis. However, I want you to forget the axis for a second. It doesn't matter. It doesn't matter. I can take this as positive as long as I take this as negative. Okay, so it doesn't matter. I can choose this to be positive and that to be negative. That's all right. So it doesn't matter as long as you realize that they are opposite each other and therefore they will have opposite charges. Now I want to talk about this briefly before I move on. Notice something here. The momentum of the system is conserved. What does that mean? What does it mean to be conserved? It means it adds to zero. Momentum 1, oh sorry, I'm not going to suddenly change the sign for momentum. P1 and P2. Here's momentum 2 and here's momentum 1. What do you notice about them? 55 and negative 55. What does that mean? It means if I add P1 plus P2, it will equal 0. They are conserved, right? Momentum is conserved. Over here I have 55, over here I have negative 55. So they are conserved. That's what that means, conservation of momentum. Let's do another problem. Hopefully it'll be slightly more clear. Okay, so here we have a follow-up. Calculate the final velocity of each canoe, given that the total mass of canoe 1 is 130, and the total mass of canoe 2 is 250. Use the results to determine whether the velocity is conserved quantity. Okay, I can tell you right now velocity is not a conserved quantity, but momentum is. Let's have a look. So calculate the final velocity of each canoe, given the total mass is of 1. So, okay, so I'm just going to write, I'm going to start labeling stuff. So this is question 30. M1, which means the mass of canoe 1, equals 130 kilos. And, excuse me, and the total mass of canoe 2 is 250 kilos. And that makes sense. There's more people on that one. Use your results to determine whether the velocity is conserved. The final velocity of each canoe. Oh, okay, so we do have the force, which in this case, is it 46? No. Yeah, so it is 46, and in this case we decided that that's going to be negative 46, and that one is 46. And the momentum, we worked it out to be 55, right? P2 equals 55, while P1 equals negative 55. Once again, it doesn't matter as long as you keep the signs on the right side. Like, you stay consistent, negative here, negative here. And what do they want again? They want velocity. Well, remember, momentum equals mass times velocity. We have the momentum, negative 55, and that equals mass times velocity. Let me just write that in here somewhere. Momentum equals mass times velocity. Hopefully you remember that. So that's going to be 130 multiplied by v, negative 55 divided by 130, and that equals negative 0.42 meters per second. Obviously, the velocity, so this is v1. This is the velocity of the first canoe. Now I can tell you right now, the second canoe is going to have a much lower velocity because it has a bigger mass. Let's work it out. I'd love for you to work it out. Pause the video, work it out, and then tell me what you get. So here, this time we have 55 divided by 250, so it's going to be nearly 0.21 or something, 0.22 meters per second. And as you can see, the velocities are not conserved. How do I know that? Because remember, how did we know that momentum was conserved? When we did P1 plus P2, it equals 0. This time though, let's do it again. I'm just going to write this properly. This is P1 and this is P2. P1 plus P2 equals 0. How? Negative 55 plus 55 equals 0. That means momentum is conserved. That means momentum is conserved. Good. Now let's look at velocity. V1 plus V2. Does it equal 0? No, it does not equal 0. Does not equal 0. How? Look, minus 0.42 plus 0.22, you can see it equals negative 0.2. So what does that mean? It means it does not equal 0 and therefore it is not conserved. Velocity is not conserved. It can change. Okay, this is just a long way of proving that. Okay, right. We'll be right back. Okay, Bismillah. So let's move on to the next problem now. Just need a wee moment to get rid of all of this. We certainly need the space on the screen to be able to work out the next problem. So just remember, momentum is conserved, but the velocity is not necessarily conserved. And how do we know that? Well, momentum adds up to 0 within a system, but the velocity does not necessarily have to cancel out and add up to 0. Alright, so what does the next problem say? What is the final momentum of each canoe if they are pushed apart with a force of 56 newtons? Okay, so let's say this time the force is equal to 56 newtons, not 46, but 56. Okay, and the time is 1.3 seconds. So whenever you see the time, that is a dead giveaway that the question wants you to use impulse in most cases. So that's going to be the change in momentum. Obviously, in this case, the change in momentum is equal to final momentum. Why is that? Because remember, we have started from 0, from static. So it's only the final momentum that really matters, Pf minus Pi, but there is no Pi for either canoes because we already said that it started from 0. it wasn't moving. So Pi is equal to 0. So it's only Pf. Okay. We also know that change in momentum is equal to force multiplied by time. And so over here it also equals force multiplied by time. The only thing we have to remember is that obviously they will have different signs. So I'm going to go with negative over here. So in this case it's going to be negative 56 multiplied by 1.3, whereas over here it will be 56 multiplied by 1.3. I don't think we need the triangles anymore. I should be able to do this in my head. That's 77. No, 73. I was way off. 73. And over here it will be negative 73. Okay. Right. That is, sorry, that is 30, not 31. That is not 30. That is 31 now. Okay. So right. Let's go to 32. 32 says two skaters stand at rest in the center of an ice rink. So an ice rink is like an ice lake, you can call it, like a swimming pool that's frozen over, and then people skate on it. Okay, I'm sure you've seen it. There's one in Avenues. Is it in Avenues? There's one in Marina Mall. And of course, there's one in Kuwait City that's really, really big. So ice rinks are pretty cool. Anyway, so here we have two skaters at rest, the center of an ice rink when they push off against each other. Here we go. So we have one skater over here and they push off against another skater. And of course, they push each other apart. So the one skater weighs or has a mass of 45 kilograms. M equals 45. And this one has a mass of, we're trying to figure out the mass of this one. Easy. Okay, acquires a speed of 0.62 meters per second, and the other one is a speed of 0.89. Notice we're talking about speed, not velocity, but we also know that it's going to be in opposite direction. So they are opposite to each other. If it was velocity, you'd have one positive and one negative, but since it's speed, it's just the magnitude. Anyway, we know that momentum is conserved. So the momentum of this person, P1, is equal to the momentum of this person, which is P2. So that's what we have to work with. So the momentum of the first person is going to be mass times velocity, which is going to equal 0.62 times 45. 27.9. This one here is going to also be 27.9. So now that I know that, I don't know what the mass is, but I know that that's 0.89. In this case, I do know both quantities. In this case, I don't. So I'm trying to figure out mass. So it's going to be mass is equal to P over V. Is it? Am I doing this right? Yes. Which is going to be 27.9 divided by 0.89, which equals 31 kg. 31 kilograms. Okay, That is question 32. So what I did here was I used the law of conservation of momentum. So because I know that momentum is conserved and I know that P1 equals P2, I figured out what P1 is, and therefore I knew what P2 was, and I know the mass, so I can work out the velocity. Let's have a look at number 33. A 92 kilogram astronaut holds on to 1,200 kilogram satellite. Both are at rest. See, you got to look out for these keywords. So that means they start off at 0 relative to a nearby space shuttle. Interesting. The astronaut pushes on the satellite, giving it a speed of 0.14 meters per second, directly away from the shuttle. Very good. And then the astronaut comes into contact with the shuttle 7.5 seconds later. They're being very sneaky. Okay, so the hardest thing about this question is trying to actually understand what's going on. So here we go. And what is the distance? Yeah, I knew it was going to be about distance. So right, so here's the shuttle. I'm going to try and draw a spacecraft. Okay, so this is the space shuttle, right? This is the space shuttle. We have an astronaut over here. And what they did was they pushed away a satellite and what happened? Giving it a speed of 0.14. So what happened was the astronaut pushed away the satellite, giving it a speed of 0.14 meters per second. And the satellite has a mass of ms, which means mass of satellite, equals 1,200 kilograms. So of course momentum is conserved, so we know that P1, or in this case momentum of satellite, is equal to momentum of astronaut. Momentum of satellite is equal to momentum of astronaut. We know that. And we also know the formula for momentum is equal to mass times velocity. So momentum of satellite equals 1,200 times 0.14. 1,200 times 0.14, which is 168 newtons per second, or kilograms dot meters per second. Now this is going to be the same as the momentum for the astronaut. So we know that PA is equal to 168. Okay, so what are we trying to work out? We're trying to work out the distance, right? So the first thing we need to work out is the velocity in order to work out the distance. So the velocity is going to be, we know the mass of the astronaut is 92 kilograms, and we know that the PA is going to be, once again, mass times velocity. So let's work out the velocity, which is going to be PA over m, right? So velocity is equal to PA over m, which is equal to, all right, let's have a look. So we know PA is going to be 168, the same as the satellite, and we know the mass is going to be 92. So it's going to be 1.82 meters per second. So what this is saying is that the astronaut is moving back with a speed of 1.8 meters per second. That's not the answer though. The question says, what is the initial distance from the astronaut to the shuttle? So they want to know this distance here. How do I work out the distance? Well, velocity equals distance over time. So we have the velocity of the astronaut. We just worked it out. Velocity equals 1.82, or speed, meters per second. And we have the time, which is equal to 7.5 seconds. So we can work out the distance. It's just that multiplied by 7.5, which is equal to 13.695 meters. Now this is when we start looking at significant figures, 2, 2, 2 across the board. So really we're just going to go with 14 meters. The answer is in fact 13.7. Okay, so velocity equals 1.82 multiplied by 1.82 multiplied by 7.5, which is 14 meters. Okay, because it's the two significant figures. Okay, hopefully that wasn't too hard. Okay. Let's do some of these. Explain if the total external force acting on a system is zero, what can you say about its total momentum? It's not going to change. The momentum is not changing. If the total external force is zero, it means there is no change in velocity. It's either stationary or it's moving at constant speed. Either way, V1 equals Vf. V final means the same as V initial. So that means the final momentum is equal to the initial momentum, which means there is no impulse. So there is no change in momentum. So 34, no change in momentum. No change in momentum, which just means no impulse. No impulse. No change in momentum. 35. Internal forces can change the momentum of individual objects within the system. Yes. How do they affect the total momentum of the system? No effect. Remember the example I told you about. You're on the plane, you start jumping up and down. Yes, your momentum has changed. You started off by sitting down, and then you were jumping, so you had a speed, and therefore your momentum changed. Or let's say you're on a train, you were standing, and then suddenly you started running. Your momentum changed, but overall, the momentum of the train wasn't affected. It doesn't matter what goes on inside you. It doesn't matter what goes on inside the system. The momentum of the system stays the same. You start running, your heart rate starts going up, your blood starts flowing more. Of course, the momentum of your blood changed. Does that change your momentum? No. Internally, whatever happens does not change the momentum of the system. Okay? So no effect whatsoever on the system. 36. Identify two ice skaters at rest in the center of an ice rink. Push off each other in opposite directions. Identify the system in which the momentum is conserved. And list internal and external forces acting on the system. Okay, so just like the example we mentioned before. So here's one ice skater and here's another, and they like to push each other. So when they push on each other, and of course they are in an ice rink, which is a swimming pool that's frozen over, and there's very little friction. So when we are talking about this system, we are talking about those two. That's the system. That is the system. So identify the system. The system is made up of the two ice skaters. That's it. Okay. And where the momentum is conserved. So basically, P1 over here is equal to P2. His momentum is equal to his momentum, or her momentum is equal to her momentum, because they are part of the same system. Okay. The internal and external forces. So the internal forces is the push from this person against the push of this person. Those are the internal forces. And of course, you push on them, they push on you back, Newton's third law, and you end up getting pushed back. The external forces, however, if you think about it for a second, there's air resistance, because if you're moving back, you're moving through fluid friction, which is, there's air resistance, but there's also friction with the ice, and that is external forces. Um, if it's completely frictionless, it wouldn't affect them whatsoever, but in reality, the ice will have friction and will slow them down. So that is an external force, okay? Otherwise, they would not slow down. Remember Newton's first law? An object that is moving does not want to stop, and an object that is stopping does not want to start moving. It's called the law of inertia, the law of stubbornness. So basically, in this case, that is an external force. The friction with the ice, the air resistance, all of those are external forces. Okay, question 37. Assess an object resting on a frictionless surface is struck by a second object. So this is very much like our example just now. I'm tempted to use ice again, so I'm going to. Okay, so here we go. An ice rink. We have an object resting on it. And it is struck by another object. So object A is struck by object B. Is it possible for both objects to be at rest after the collision? Is it possible for both objects to be at rest after the collision? No. Why not? Let's see. Object B has a momentum, right? So object B's momentum is going to be mass times velocity. Let's assume the mass of object B, I came up with it. Let's assume that the mass of object B is 1 kilogram and the velocity is 1 meter per second. We're just going to keep it really simple. That means the total momentum is going to be 1 kilograms dot meters per second. So obviously after object B strikes object A, and they are part of the same system, object A has to start moving, or if object A is really, really heavy, then object B will bounce back, but it will have to keep moving because the momentum is conserved. You can't go from momentum 1 to a momentum of 0, which is what they're saying. Can both objects be at rest? No, of course not, because it means this guy will have a velocity of 0 and this guy will have a velocity of 0. That's an impossible situation. You can't go from a momentum that has a value to a momentum that has no value. So no, you cannot. No, because momentum is conserved. So there is momentum, the object was moving, it had velocity, it has a mass, therefore it has momentum. You cannot go from that to 0. Something has to be moving afterwards. Next, is it possible for one of the objects to be at rest after the collision? Yes, that is possible. As I explained, object B, if it hits object A, then object A can start moving, like Newton's cradle, or like when you're playing pool or cue club or whatever. One ball hits the other ball and the ball continues moving. The one doing the hitting in the beginning can actually go to rest while the other ball continues moving. So that is possible. Yes, they don't both have to continue moving. Or in fact, if the other ball is very, very heavy, then the first ball will bounce back. So that's definitely possible, that because still momentum is conserved in the system. If this object is moving and it hits the other object, then this object can start moving while this one stops. That is possible. That's what it's saying here. Okay, question 38. I'm going to go over here for 38. Explain if you drop your keys, their momentum increases as they fall. Is the momentum of the keys conserved, or does the momentum of the universe increase as the keys fall? Explain. Mm. Okay, so this is the same situation as if you're on the plane or you're on the train. We're all in this universe. This universe is a closed system. The whole universe is controlled by God. Okay, so all the momentum in the universe is conserved. It doesn't change. So does the momentum of the universe increase as the keys fall? No. Okay. It's exactly like me running on the train. If I run on the train, am I increasing the momentum of the train? No. Okay. I'm an internal force. So the keys, yes, they do increase in momentum because there is an external force acting on them, which is gravity. The same way, if I start running, I am I have an internal force that's causing me to run, and basically there is a difference in my momentum, but the train's momentum does not change. And so the keys, yes, they start speeding up because of the gravity, but the momentum of the universe is still conserved because gravity and the keys and everything is within the universe. I hope that makes sense. It's a little bit tricky, but just remember it's all part of the same system. Let's go to 39. 39, we have calculations to do. Two canoes are touching at rest on a lake. So the same situation as the two skaters on the ice rink. Now this time we have canoes on the lake. So we're assuming very little friction, obviously. Right. What's happening? And they are at rest, which means they are not moving. The occupants push away from each other in the opposite directions, giving canoe 1 a speed of 0.58. So we have two canoes. Canoe 1 and canoe 2. Canoe 1 has a speed of 0.58 meters per second and a mass of 320 kilos. Canoe 2 has a speed of 0.42 meters per second and a mass unknown. This is what they want. Remember, P1 equals P2. Momentum is conserved. So 320 times 0.58, 186, 185.6. That is the momentum. All I have to do is divide it by the speed, 0.42. Now that I know what P2 is equal to, which is 185.6, I can work out the mass. Because remember, P2 is going to equal mass times velocity. I have the velocity. I need to work out the mass. It's going to be 185.6 divided by 0.42. So it's going to be P2 is equal to, oh no, sorry, M2, which is mass of canoe 2, is equal to P2 divided by velocity, which is equal to 185.6 divided by 0.42, which is equal to 442 kilograms. How many significant figures are we working with? 2, 2, and 2. 440 kilograms. That's the mass. This is 39. Let's go to 40. A 94 kilogram lumberjack stands on a 1,200 kilogram log on a pool of water. Interesting. So we have a person, a lumberjack, which is a person that cuts trees. He usually has an axe. So I'm going to draw an axe. That's an axe, not a flag, okay? Right. And they are standing on a log on the river. Is it river? Does it say what? No, on a pool of water. Initially, the lumberjack and the log are at rest, which means they're not moving. So the P initial is 0. The lumberjack then starts jogging towards the shore along the length of the log. Okay. If the lumberjack's relative speed to the shore is 2.2, what is the log's speed to the relative to the shore? Okay, so once again, we have P1, which is the lumberjack, and P2, which is the log. And P2 is equal to mass times velocity 2, while P1 is equal to mass 1 times velocity 1. And we know that the mass of the lumberjack is 94, and he is jogging at 2.2 meters per second, which means P1 is equal to 206. Am I getting? Yeah, so 206.8. I'm not going to do any rounding just yet. Remember, we do the rounding at the end. Kilograms dot meters per second. This is P2. This is P1, but it's also P2 because momentum is conserved. Momentum is conserved. So this is going to be equal. So now P2 is equal to 206.8, same as P1. And we know that the mass is equal to 1,200. So we need to work out the velocity, or the velocity or the speed? The speed. So we don't even have to worry about signs. Of course, if it's velocity, it means it's going to be negative because it's going to be facing away from the shore. The person walks forward or jogs forward, and the log goes backwards. But since they're asking for the speed, they're just asking for the magnitude. So it's going to be, remember the formula, PMV. I'm looking for V, so it's going to be 206.2 divided by 1,200, which is going to be 0.1723333 meters per second. How many significant figures are we working with? Once again, it's two significant figures, so 0.17 meters per second that way. You don't have to include the direction, they just wanted the speed. But that's the answer. Okay. Number 41, a young hockey player stands at rest in an ice skating rink with the helmet. They threw the helmet. What is the mass of it? Okay. I'm going to let you do that one yourself. I think, yeah, I'd like you to do that one yourself. And if you're not sure about it, you can send me a message on Teams. But I'd like you to do that one yourself, please. Okay. Thank you. That is all from me. And I just wanted to remind you all to please use the last 10 days of Ramadan because of course, their value. Jazakumullah khair, everyone. May Allah bless you and may Allah help you with physics and all of your subjects. Take care. Assalamu alaikum wa rahmatullahi wa barakatuh.